So, there's a lot of stories going about. People have a lot of questions. A lot of the new images coming back from JWST, depending upon the level of analysis, what seems to be coming back, a lot of things don't quite seem to fit. But I'm gonna make a claim here that Einstein was right. Now, a lot of people will say, that's a totally simple conjecture, because Einstein's been right about a lot of things. He's been wrong about things. There are things that we know we do not yet have the full story. We have pieces of the puzzle. We're using our best approximations, the methods we have been using to help explain a lot. But I'm going to make a claim that Einstein's original formulation of general relativity was correct. Because in his mind, for whatever reason, he had an image of a steady state, a universe, if you would, a realm of persistence that would continue on, would be able to self-propagate. And then at one point he's like, oh, that was totally wrong. Why? Because we had observations at the time that seemed to contradict that. But now we have new observations with our new tools of measurement that seem to be perhaps, according to some, uprooting a paradigm. You have folks making claims like, the Big Bang never happened. I would say the more appropriate question is, according to our best observations, what is the Big Bang to our relative observer frame here? Because I'm going to make a claim that I colloquially call eternal, if I can spell it right, eternal cyclic cosmology. Yes. Talking and writing are not always the easiest things to do at the same time. But what's the claim here? According to many of the principles of GR and many people, we could try to imagine our realm, so to speak, as the n hypersphere of maximal volume, perhaps a Riemannian sphere, a pseudo-Riemannian manifold. Again, do we know exactly what's going on? No. But I believe with our levels of measurement, the computational power provided by computers, large language models, neural networks, and just the internet in general, people being able to come together, collaborate, have conferences online, in real life, that we can actually start to figure out what's going on. So, according to one of the models that had first put out there in 44, I had read through it, and it took me a while. It took me several times of reading through it and learning more to kind of get a picture in my head. And this is conjecture on my part. This is conjecture on my part, but I think it might explain a lot. So one of the interesting things that came up with is, according to the parameterization, to the best of our knowledge and what we've seen is, once you have the parameterization of the simplest universe, at some point it needs to collapse and project out into what we know as the n hypersphere of maximal volume, basically our four-dimensional space-time, if you would, because space and time seem to be just woven together in such an important way that there's some folks that say, and I'm biased of this, tend to believe that space and time, they may be discretized. Like there may actually be an infinitesimal, which is actually interesting because calculus is actually known as infinitesimal calculus. So very often we might treat something as a zero, except in certain instances. So what we're going to say here is, based upon some of Thad's calculations in the book, that n hypersphere, it is actually finite, not infinite. And that seems like a completely crazy concept. It's not like any previous ideas in history have ever been heralded as crazy. But I'm going to make the claim for this conjecture that this n hypersphere is approximately 10, we don't need an A, 10 to the 32 meters. That's really freaking huge. Now, if that were the case, because some more recent observations, it's kind of interesting because it kind of looks like our universe as we know it seems to have zero curvature. Plus or minus a waving hand right there. We'll say that. It looks flat. It looks flat. Now, with our current observations, we can only see out about 93 billion light years. That's really big, but that's 10 to the 26 meters. That's 6 orders of difference, about 168,000 times. So, again, if this calculation is correct, that means to our observations as little folks out here in the Milky Way at some point, yeah, that would explain the observation there. But the claim is going to be if we can get to a large enough scale at some point, we observe positive curvature. So what am I saying? How could this explain other things? And again, conjecture, but the other claim is there is a point tying everything together. Some may say almost a knot in the space-time fabric, right in the center here. And that's approximately 10 to the negative 8 meters. Really freaking small, smaller than a grain of sand. But it is an infinitesimal. The claim is there is something that would be in the form of the complement of the hyperbolic figure 8 knot. Is basically you have this knot here and it's small, but there's an articulation and there is a vortex throat there in that it has the ability to suck things up, so to speak, and send them back out. So just to kind of model this in a way rather than going through just all the math and everything, just something to consider. So if this was true, here's what my mind is conceptualizing it as. Okay, so if there was to be a Big Bang, you would have the emission of a whole bunch of, let's say, hot quark gluon plasma, basically the building blocks of our universe being spewed out. Because right now it starts off with general subjects like quantum fluctuations. Like the hand waving is built in there, which I kind of find humorous because it almost feels like a wizard. And it's like you have an infinitesimally small singularity that everything that we know bursts out from in an infinity. I'm like, that sounds like a miracle. And that's hard for me to grasp. So I'm like, okay, I'm not going to say necessarily exactly how we got here. I'm just going to try to go over more of the persistence of what I'm going to claim the point we're at. So if you have what to our relative observation would be a point, you could have a whole bunch of hot particulate, call it matter, baryonic matter, oscillation. You're going to have a whole bunch of that energy spewing out. Now, if it's spewing out, and especially if there's any type of articulation or rotation here, we had the concepts of the ether. People are talking about superfluidity, and now the exact solution, I don't know. But we're basing this off of kind of the laws of nature as we know them now. So if you have all this particulate spewing out here, at some point, at least according to our models, it seems like it starts to cool down. And as it cools down, it forms protons, electrons, neutrons. And then you start to have the binding together of some of the more simpler elements. And as gravity takes hold, it starts to bring those simpler components back together and everything. And you start to have gas starting to come together. So then it starts to form stars. And then those stars start to come together. And you get galaxies. And as you get these galaxies, I'm just going to try to conceptually spin it what I would assume was the right way. So you start to have all these galaxies start to forming all over the place. And as these begin to populate, again, gravity will take over. And as these galaxies come together, they're going to start to form larger and larger groups, clusters, if you would. And as these clusters begin to form, they form into larger clusters, they form into superclusters and everything. And again, according to many major imaging and everything, the theoretical assumption is you're going to have a super dense point in those places that we colloquially refer to as black holes. So black holes, that's an interesting discussion in itself. I've completely speculated. A lot of my thoughts on that seems to have been changed. Do I know if they're correct? No. But again, it might explain a lot. That's for another time. As we start to have these large galaxies come together, at some point, given enough time, gravity will still probably come, and they're going to get larger and larger. And we've already had, the theoretical limit was like 50 billion masses of the sun. Well, according to some observations now, people are conjecturing maybe it's 66 billion. Is there actually a limit? What I'm going to say is, I personally don't think there's a limit. That's just my personal opinion about that. But if you start having all this matter, all these coming together, maybe we can get some, perhaps what we may colloquially call a hypermassive black hole. Things larger than we could just imagine. There be monsters out there, I claim. So whether it's in this form or just a galaxy cluster, as you get all this immense amounts of mass cycling through, because we're going to assume some form of thermal dispersion to even things out, the whole entropy thing that a lot of people can't even agree on what exactly entropy means. We have dimensional boundaries and everything. But the interesting thing, we were actually talking about this a little bit last night, Echelon, is entropy almost kind of seems weird for physics. It's like, well, at one point, I forget who it was, but somebody said, well, these equations look like entropy, just call it entropy, because nobody knows what entropy is. And it's like, that's weird. Again, some people seem to put some hand waving, but again, there are actual rigorous calculations to this. And it's funny because you were like, last night within programming, well, if we're running scripts and stuff like that, well, that kind of seems to be things changing. Entropy is essentially the continued disorder of things. So what I'm going to claim is you have a whole bunch of matter. If you have some type of vortex articulation where it's sucking things in and spewing them out, what happens if you were to get a whole bunch of matter going in through an incredibly small yet finite volume? If at that point it's being compressed and going under some very complex articulation at the center of our realm of persistence itself, I mean, wouldn't that be the equivalent of just compressing something and then kaboom? Some may view that as a big bang. And then the cycle would continue. Because it's also interesting in that, I know Professor Wolfram, he had been discussing a lot about the work on the second law of thermodynamics. And within the realm of the laws of thermodynamics, it is actually conjectured that they say a perpetual motion machine, so to speak, it can't exist, well, except for the third type. What is the third type? The third type would have to be a system with a boundary. There's a boundary at some point, and it would need to have maximal efficiency. Some may say the most efficient form of being able to persist. And since the Giesecke manifold is the smallest non-orientable manifold, and our claim is we have a double cover of that, and there's a very complex articulation going on. If the cycle continued, if matter comes in, whether it's black hole, whatever it is, if there's a point dense enough, cinching the cosmos themselves together at a point that could bring them in, expel them out, I sit back and Professor Einstein, he believed in the cosmological constant. He believed in, now we didn't know about all these different geometric states. We didn't have the computational power that we do have now, but there was something in his head and he worked on it up until the day he died, looking for that right Calabi-Yau manifold, trying to get things to line up. I'm going to claim Einstein was right because the cosmological constant, it tends to be lambda. So we have lambda. And that's, it could be, well, it could be plus, it could be minus. Well, I just look at this as, well, that's going to be what's going on with our bulk here. What if it was plus and minus? Almost a source and a sink. Kind of like electromagnetism. Just because if we're going to look at those equations are very beautiful and explains a lot, and we try to extrapolate using models that we know, the simplest models that we know, to try to explain our observations. So what does this have to do with JWST? Well, JWST is measuring some galaxies that, according to our model, we assume approximately 14 billion light years. Okay, we believe that galaxies with a certain level of redshift so far away that if they appear as developed as our Milky Way, or perhaps even more massive, more developed than our Milky Way, that's not something we were expecting. How could we explain this? And we're trying to tweak our models. I'm saying, no, most of our models, they look to be pretty dang good. They seem to be right. What parameter might we be not accounting for? So if we're going to assume that if we're over here at about 14 billion light years, okay, so if we were to rewind that to the point where we were at a hot quark gluon plasma, so to speak, it's, well, maybe there were other galaxies, maybe going the other way. Maybe the entire relative system, conjecture, might be a little greater than 14 billion years old. Because I look at this model, and if I were to assume as efficient as possible, if it was a potential perpetual motion machine, how could we get that? Well, it might not be within the realm of we humans to do so, but is it within the realm of nature itself? If it was possible, how would we go about that? And that's this claim right here. Just because if the time was greater, if you just adjust that one parameter, at that point it's like, well, wouldn't there be more black holes? Wouldn't there be more neutrinos as well? Like forms that we actually know, like the dark matter that we know of exists if we did have a model, and if it did happen to be greater the amount of time for the entire system than 14 billion years, might explain a lot. So just kind of want to put that out there. Do you want to go with that?
Sure.
All right.